material. We had Friday, we didn't have class, but we're going to pick up where we were on Wednesday, which was we had just introduced generalized through and across variables. So they had symbols script F for generalized through variable and script V for generalized across variable. And then their integrated versions, which were script H and script X. But I don't really know how to do script, so I'll do it like that. Oh, that's pretty good. So we had just introduced those, and now we're going to finish off chapter 1 by looking at these analogies among the different energy domains in more detail. So we've talked about the analogies among the different variables now. So across variables are like voltage and velocity and angular velocity, right? Those were our 3 across variables. So they're all in this category here. And they represent quantities that have distinct points in the lumped parameter system that they could be measured at. And they're always referenced to 2 different values. So there's a reference value. Whereas for the through variable, it flows through the different elements. These were current, force, and torque, right? And we also had the integrated version of that. So that was what we had last week, and now we're going to generalize not just the variables that we use to describe these systems, but also the elements. So we can categorize the behavior of one-port elements, electronic elements, mechanical translational elements, mechanical rotational elements considered thus far. So one-port elements, so we talk about masses, springs, capacitors, resistors, inductors, dampers, all of these different things. So we're going to put them into these different categories. So in the following sections, we consider 2 types of energy storage elements. So we have 2 bins for energy storage elements, and then we have dissipative. We have only 1 bin for that, and source, we just have 1 bin for that too. So here we go. A-type energy storage elements are the first type we'll consider. An element that stores energy as a function of its across variable is called an A-type energy storage element. Sometimes we call it a generalized capacitor because a capacitor is an A-type energy storage element. So we have clearly the capacitor is one of these. What about from the mechanical system? What's the analog there? What is it?
Spring?
So actually, it's going to be the mass, and that's because we're going to have the energy stored in the kinetic energy, which is 1/2 mv squared. Remember that the energy for the spring, linear spring, was 1/2k times the force in the spring squared. Even though you've often seen 1/2kx squared. But that's not, well, I tried to give an argument for why we don't look at it that way. Okay, good. And then also the rotational moment of inertia is kinetic energy 1/2 j omega squared. So the energy is stored in its across variable omega. All right, so for generalized through variable f, across variable v, integrated through variable h, and integrated across variable x, the ideal linear constitutive equation is that the integrated through variable h is equal to some constant c, which we call the generalized capacitance, times v, the generalized cross variable. So generalized capacitance for a generalized capacitor makes sense, right? Differentiating the constitutive equation with respect to time, the elemental equation is
C F equal D with B over D.
Yeah, and so we were going to rearrange it so 1 over c is on this side, and we have dh dt. So h is the integrated through variable. So if you take the time derivative of it, it just becomes the generalized through variable f. So this equation is like if we had an electronic circuit, it's like for a capacitor, dVc dt equals 1 over c IC, right? Or if this was a mass, this is going to be dVm dt, velocity of the mass, m, equals 1 over m times Fm. F equals ma. Okay. But we're using the generalized through and across variables. This is our elemental equation. A-type energy storage elements considered thus far, capacitors, masses, and moments of inertia. As with generalized variables, the analogs among elements are more important than our generalized A-type energy storage elements. So this concept of like a generalized A-type energy storage element isn't so important as recognizing that there are these analogs, right? That a mass is like a capacitor, or that a moment of inertia is like a capacitor. That's really the big takeaway here. We are going to use this terminology, though. So in Chapter 2 of the electronics part of the course, in Chapter 3, we had this process for analyzing circuits, right? And we are steps 1 through 6 that we had. We're going to come up with a new list that allows us to do that for any type of dynamic system, not just for circuits. And we're going to use this really nice procedure that allows us to write only the equations that we need. So the elemental equations that we need, there's going to be something like the Kirchhoff's current law, like KCL, for this too. But it'll tell us which ones to write instead of just, you know how we were often just writing like all of the possibilities and then like hoping we could wade through the equations. We will write down the exact number of equations that we need, and that helps us solve things. It's a lot easier to solve the systems when you follow the procedure that we're gonna follow. Also, once we get there, so I have a former student. Does anybody know Cameron Devine? Yeah. He's working on his PhD up at UW now, and I still work with him on some research. Anyways, he graduated from here a couple years ago, and he wrote this really nice online solver tool that is going to let us write down our elemental equations, essentially our KCL, KVL equations, and then hand it to this nice website that will then return to us the differential equations. We won't have to do any of the algebra. Or what's probably the better way to use it is to check our algebra, right? So we'll think of the algebra part as like a machine that you can automate the process, but often we get lost in it because we're not really good at automated processes. Personally, I suck at them. I won't speak for you. Well, your test grades do, but sorry. Too soon? Too soon? Oh man, it's just like, we gotta keep it light though, right? And I took grades really, really seriously when I was in school. And I feel like it's really easy to do that. But that like hopefully you guys don't make the same mistakes I did, because I was too worried about grades, and sometimes I didn't focus on like just learning the material and like having good balance in my life. I'm still bad at that. I still haven't learned my lesson. Bad at balance. I think that like one day I'm gonna just like become a yoga instructor or something. Just like quit everything, become a yoga instructor, and just talk about balance and like energy. And that'll be it.
Just have like 2 credit class yoga for engineers.
Right. You're acting sort of like an energy storage element right now. We just really need to like let it flow, through your through variable. Just let it flow. Yeah. Discharge. The capacitor. Okay. So, T-type energy storage elements. An element that stores energy as a function of its through variable is called a T-type energy storage element. Sometimes we call it a generalized inductor because, you guessed it, an inductor is a T-type energy storage element. And try to be straightforward with these namings. The ideal linear constitutive equation is that the integrated across variable x is equal to L, the generalized inductance, is a constant, times the through variable f. Differentiating this with respect to time, the elemental equation is we also rearrange it a little bit. We get df dt equals 1 over L times, so the time derivative of the generalized across variable, the integrated generalized across variable x is just v, script v, right? The across variable. Great.
What's that website you were talking about?
So it's like kind of working right now, but it's like got some layout issues. Shoot me a message on Slack and I'll send it to you. He's hosting it right now on his page because he's like under construction kind of thing, but it is still functional currently. It's just like it looks weird. So yeah, shoot me a message and I can send it out. It's not quite ready for prime time, but you can still use it in the meantime. It's pretty cool, and I'll do a little tutorial on how to use it once it's up and running. You can do something similar. I wrote a package that lets you do that in Mathematica, based on a package by somebody that wrote it before me, and then yeah. So there are other iterations, but I really like this tool that he built because it's like totally. Like you can just do it all in the web browser. You don't have to have any software installed, no coding. Just like enter the equations and then hit calculate and then spits it out. And it has examples on there. It's pretty nice. He did a really nice job of it. Yeah, because so they use the same process for constructing system models at UW. They have the same curriculum, essentially very similar to what I am developing. A little different, but yeah, a lot of similarities. They use linear graph models too, like we're learning today, actually. All right, so great. So the ones that we've been exposed to so far that are T-type are inductors and springs, so translational and rotational springs. So these are considered to be analogous then. An inductor is kind of like a spring. Conveniently, remember that the inductor looks like that in a circuit, and a spring looks like that in the schematics. So that's the one easy way to remember it. The curly Q's go together. If I had made that rhyme, it would have been cool. Okay, D-type energy dissipative elements. An element that dissipates energy from the system has an algebraic relationship and has an algebraic relationship between its through variable and across variable is called a D-type energy dissipative element. Sometimes we call it a generalized resistor because, I know, a resistor is a D-type energy dissipative element. So that's why we call it a generalized resistor, because resistors happen to be one of them. Other ones are dampers, so rotational and translational dampers. They dissipate energy from the system. In both cases, they dissipate it into heat. So for the constitutive and elemental equation, we have that the cross variable is equal to R times the through variable, where R is called a generalized resistance. It's some constant for a given element. Once again, the important thing is to recognize that there are analogies here between the different, or among the different dissipative elements. And finally, we have sources. So an ideal through variable source is an element that provides arbitrary energy to a system via an independent through variable. So independent of the system, you can connect it to anything and it'll provide that through variable happily. Okay? The corresponding across variable, and this is a typo, just to scratch that. The corresponding across variable depends on the system. Current, force, and torque sources are the through variable sources considered thus far. So current source is a through variable source, a force source is a through variable source, and a torque source is a through variable source. The reason that those are all through variable sources is that current, force, and torque are all through variables. So if they provide those, they're through variable sources. An ideal across variable source is an element that provides arbitrary energy to a system via an independent across variable. So same thing, but for across variables, right? Corresponding through variable through the element depends on the system that's connected to. Voltage, translational velocity, and angular velocity are the across variable sources considered thus far, and that's because voltage, velocity, translational velocity, and angular velocity are the three across variables we've considered thus far. Okay. Any questions about this? You guys, you know how I've been like talking about how any questions? This is like David S. Pumpkins from Saturday Night Live. It's a skit, and nobody knows this reference, but it's hilarious. It's a Halloween thing. And I was at a bar in Olympia on Saturday night. I was feeling better. I was like, I'm gonna go have a drink with some friends. And everybody's dressed up, but like I'm not. But like it's not really, we weren't going to like a costume party. It was just like going out, and most people were dressed up though. And I saw somebody wearing a David S. Pumpkins costume. Like, so it's like a black suit with orange jack-o'-lanterns all over it, and like a crow. It's pretty great. I was impressed. I was like, nobody else probably knew what he was supposed to be, but I was like, oh, that's a great costume. I didn't actually say that because, you know, I'm shy, but I'm actually not shy.